Okay guys, this is part 2 for our unit on liquids and solids. If you haven't watched part 1, you need to go back and watch it. Okay, because we are using what we discussed yesterday for today's video. Objectives. We will be able to draw a phase diagram of a substance given appropriate data and use a phase diagram to predict which phases are present at any given temperature and pressure. We will also predict the type of solid, molecular, covalent network, ionic, or metallic formed by a substance and predict its general properties. I hope you have already completed your quest intermolecular attractions. If you haven't, what we are going to discuss today will tell you what exactly you need to know to complete that homework. Alright, I need for you to listen carefully. That's where we stopped last class. Factors affecting the boiling point of a substance. Factors affecting the boiling point. If you look at that diagram, this is temperature versus pressure. Or pressure versus temperature. Pressure versus temperature. If you look at this is diethyl ether, this is ethanol, this is water. As you can see, you need a higher temperature to vaporize water than you would need for ethanol. You need a higher temperature to vaporize ethanol than you would need for diethyl ether. And we will discuss in a few minutes why you need much higher temperature to vaporize water than the others. As you know, I have told you before, chemists do not like to use curves. They do not like to use exponential relationship. So there was a guy called Clausius Clapeyron, two of them. They came up with a graph so you can have a straight line going down. So I'm going to show you exactly how they derive it. Instead of having pressure, vapor pressure versus temperature, when you plug natural log of vapor pressure versus inverse temperature in Kelvin, it will give you a straight line going down. Here is the equation. Okay, so it is a Clausius-Clapeyron equation. Here is the equation. You have the natural log of the vapor pressure equal the negative of the enthalpy of vaporization over R, which is our gas constant. And because we are dealing with energy, that R has to be 8.314. So this is the energy R times the inverse temperature plus a constant. You do not have to worry about that constant. If you look at that graph, this is a linear equation. If you look at carefully, this is your y. This is the slope of the line. Okay, this is your m. This is the inverse temperature is your x, and then plus b. Okay, this is a linear equation. Remember that equation. The natural log of the vapor pressure equal the negative of the heat of vaporization of that substance over R, which is 8.314, times the inverse temperature in Kelvin. You don't have to worry about the C, because I'm going to show you how you will be using that equation more often. You would not be using it like that most of the time. You will use it as a two-point form. At a two-point form, that means they will give you two different vapor pressure. They will give you two different temperature, and ask you for the heat of vaporization, or they can give you the heat of vaporization. They give you one of the pressures and two temperature and ask you for the vapor pressure at that different temperature. So I could take the time right now and derive the 2-point form for you, but I'm not going to do that. I'm just going to give it to you. Okay, we could easily derive it from here. The 2-point form is, let's say we have natural log of pressure, vapor pressure 2, VAP, over vapor pressure, this is your VAP, vapor pressure 1 equal, and then since I don't like to deal with fraction, the negative, let's leave this positive. Delta H of vaporization over R times, this is 1 over T1, so I reverse this, 1 over T1 minus 1 over T2. This is what you will be using to solve almost all the problems that I have to do with this equation. They will give you one of the pressures or one of the temperature they ask you for to solve for the other one, or they can give you the linear form and ask you to form for delta H of vaporization, where you would be using the slope and solve for delta H. Now I don't think yesterday I really described heat of vaporization. Okay, we solved a problem last class. We did use heat of fusion, delta H of fusion. We also use delta H of vaporization. So what is delta H of fusion? Is the amount of heat needed to melt 1 mole of a solid at a specific temperature. Or if it's molar heat of fusion, is the amount of heat needed to melt 1 mole of a solid into liquid. Or delta H or molar heat of vaporization is the amount of heat needed to vaporize 1 mole of liquid into its vapor. Alright, and if you to help me, pull out your calculator please. Let's see if we can solve this problem. The vapor pressure of water at 25 degrees Celsius is, so let me label everything. Get ready please. This is, let's call this T1. And then the vapor pressure, let's call this, what do we call pressure? This is pressure 1. Or VAP, pressure VAP 1. And then it is in torr. Remember it is in torr. And the heat of vaporization of water at 25 degrees Celsius is kilojoule per mole. This is our delta H of vaporization. Calculate the vapor pressure. They ask for pressure, let's call this P2. At 50 degrees Celsius, let's call this our T2. Okay? So, there is one problem here. So what is R when the pressure is in torr? That means we would have to convert our pressure into kilopascal so we can use the 8.314. Okay, so let's convert the pressure in kilopascal. Let's do that. This is 23.8 torr. Let's use conversion factor. This is our kilopascal and this is torr, and we know that 760 torr is the same thing as 101.3 or 101.325 kilopascal. Okay, in my head it is easier for me to convert the pressure in kilopascal, so I won't have to change my R. So can someone tell me what is that pressure? What is it? 303.17 kilopascal. Okay, kilopascal. Let me create some space here. Alright, now let's just apply the formula. The formula says natural log of This is your P2 over P1 equal the delta H over R times 1 over T, I cross them, T1 minus 1 over T2. So natural log of, it's going to be a lot of math, guys, get ready. Natural log of, I plug my pressure 2 is what I'm looking for. My pressure 1 is 3.17 equal delta H, they gave it to me, is, okay, now we have to be extremely careful. I want to use 8.314 for my R, but this is 8.314, but that 8.314 is joules per Kelvin times moles. So why don't I change my delta H into joule? It will be 43,900. This is joules per moles. And then times, I'm running out of space. Try not to get confused with this. Times 1 over my T1, which I need to convert into Kelvin. It is 273 plus 25 give me 298. 273 plus 25 give me 298. Okay, minus 1 over my T2 is 50 plus 273 give me 323. Okay, 323. Okay, can we try to do, let's do this. Okay, yeah, you have the right side. Okay, what is the right side? Okay, can I clear everything? I can clear everything, right? Okay, let me make some space right here. So if you say this is the right side, let's write natural log of P2 over 3.17 equal, what is the right side? 1.371. Is that right? Okay, so let's go with 1.371. I think the easier things to do here, can we take the anti-natural log of both sides? Right? So we can get rid of that natural log. Alright, so this is P2 over 3.17 equal. What is the second natural log? What is e to the 1.371? 3.941. And then here we can cross multiply. P2 equal 3.941 times 3.17. 12.49. We set 12.49. And this is pressure. This is pressure. But we did convert the first pressure to kilopascal. Is that right? So this would be kilopascal. Now, let's see what the answer tells us. Okay, can we change this? Let's change this into torr to see what happened. Let's change it to torr. This is kilopascal here. This is torr. This is 101.3 or 25. This is 760. 93.7. Okay, did a great job. Great job. We did it. Okay, very good. Thank you very much. This diagram is extremely important. I went over it yesterday, but since I was using a video, it went too fast. So I need for you to listen carefully. You need to understand every single part of this diagram. Every single part of it. Remember yesterday I told you, okay, this is pressure versus temperature. You will always have your solid here, always have liquid here, always have gas here. I said yesterday, any point on this line, they are point at equilibrium, where your solid and liquids are at equilibrium. Okay, in other words, solid, liquid, it could be the freezing point or the melting point at different temperature and different pressure for that substance. Okay, so I told you yesterday, let's say this is water. If we have 100 degrees Celsius here, 100 degrees Celsius, you go up to exactly 1 atm. This would be the normal freezing point and normal melting point of water. But if I go here, this is still melting and or freezing. It's still melting, freezing. Any point on this line, it is melting or freezing of that substance at different pressure and different temperature. Okay, any point on the line. So from solid to liquid, we said it is melting. From liquid to solid is freezing. This line here, any point on this line is where your liquid and gas are at equilibrium. Okay, if it's exactly at 1 atm pressure, you go down here at 100 ml, it will be the normal boiling point of water. But any point here will be a boiling point at different pressure, therefore different temperature. We said yesterday you can have your water boil at 30 degrees Celsius. It depends on the pressure. Okay, so if you have if you go at a very high altitude where the pressure is low, you can have your water boil at a low temperature. Okay, so from liquid to gas, this is your vaporization. From gas to liquid, this is your condensation. Another point here, I need for you to look at this. That's why carbon dioxide can go, I will show you on the next pages, that's why carbon dioxide will most likely sublime. It will go from the solid to the gas, solid to gas, and then back from gas to solid is deposition. This point here is very important. Okay, this point is called a triple point. Triple point is when your solid, liquid, and gas are at equilibrium. All three of them are equilibrium. Solid, liquid, and gas, triple point, they are all at equilibrium. Another very important point here is the critical point. The critical point is the point at which it does not matter what pressure you use, you will not be able to liquefy your gas. Okay, this is the temperature, the pressure at which a gas cannot be changed into a liquid. Any point above the critical point, that's what we call a critical fluid. A critical fluid is not, it is a substance, it's between liquid and gas. It's not liquid, it is not gas. It is more dense than a gas, at the same time it is not a liquid. So they use critical fluid in different things. They can use a critical fluid in dry cleaning. Okay, in dry cleaning they use it. They use it for a good solvent. They could I think now they are even using carbon dioxide as a critical fluid in dry cleaning. So again, remember every single point in that diagram. You will have questions on that. Okay, this is the phase diagram between water and carbon dioxide. You need to know the differences between those two. The differences between those two, I mentioned yesterday. For water, you can easily see that the slope between the solid and the liquid is negative. That's why solid water is less dense than liquid water, which is very strange, because almost for every other substance, the solid is more dense than the liquid. But for water, the solid is less dense than the liquid. That's why if you put a cube of ice in a glass of water, the ice will float. It is less dense. Alright, so I need for you to really analyze those two and see the difference. I just told you a few minutes ago, this is carbon dioxide. Look at sea level at 1 atm. You cannot melt carbon dioxide. So you only can go from a solid straight to a gas for carbon dioxide. That's because the triple point is very, very high. Cannot melt it. Up to 5.1 atm, you go straight from solid to gas. So make sure you analyze those two graphs to see the difference between them. Critical temperature and pressure, we already talked about it. Critical temperature, temperature above which a gas cannot be liquefied at any pressure. And critical pressure, the only pressure at which that will liquefy a gas. Alright, even though I wanted to finish today, I did not want to make a third video, but it looked like I will have to stop here. Okay, I will have to do a part 3 next class, unless I can take 5-10 more minutes to finish this, so we won't have to have part 3. Okay, so we continue, so we won't have a part 3. Okay, let's go for it. No part 3, let's go for it. Very, very important. Intermolecular forces. It is a review for you. All the physical properties we have discussed so far, they have to do with the intermolecular forces. That's what determine the properties of the physical properties of the substances. Viscosity, surface tension, the state, liquid, solid, gas, melting, boiling, freezing. All of those have to do with intermolecular forces. So, what are the intermolecular forces? They are the forces that hold, that between the molecules. So, we studied on bonding in intramolecular forces. Those are the bonds. Those are the ionic bonds, molecular bonds, metallic bonds. But those are forces, intermolecular forces, forces between the molecules. They are much, much, much weaker than intramolecular forces. When you boil your water, you do not break the bond between H and O. You do not do that. This is your oxygen, this is your hydrogen. You boil your water, you change it from liquid to gas. You never break this bond. It is too strong. This is the covalent bond. What you really break is, I have another water here. This is H. This is O. This is H. What you really break is the interaction between the oxygen from this water molecule and the hydrogen from the other one. It is the intermolecular force. So what are those intermolecular forces? First, this is a very good diagram from your book. If the molecule is non-polar, the only force it will have is London dispersion. They call it dispersion, they call it London dispersion, they call it different names. Induced dipole. Okay, non-polar molecules have only London dispersion. But all the other molecules have London dispersion also beside the other forces they have. Okay, if the molecule is polar, if you determine it is polar, it has London dispersion and dipole. Polar molecules have dipole and London dispersion. Now there is a special case of dipole. It is a very, very strong dipole. It is very special. It exists only between hydrogen of one molecule and oxygen, fluorine, nitrogen of the adjacent molecule. Okay, this is a very, very strong type of dipole. That's what makes water behave the way it behaves, so strange from all the other substances, because it has hydrogen bonding. Now let me repeat. You do not look at a substance and see it has hydrogen and say it has hydrogen bonding. Not all molecules with hydrogen have hydrogen bonding. To have hydrogen bonding, it should have hydrogen in it and should be bonded with fluorine, oxygen, nitrogen inside that molecule and have an attraction for fluorine, nitrogen, oxygen from the adjacent molecule. Okay, another type of intermolecular force is ion dipole. Ion dipole is, for example, when you dissolve salt, you have your ions from the ionic compounds. Those ions, the positive, negative, will be attracted to a polar molecule. For example, water. You have the salt dissolved in water. The ion from the salt will get attracted to the dipole of that polar molecule. It is ion dipole. And then we have the other cases. So I need for you to remember, if we were to put those in order by strength, if we were to put them, we would put London dispersion as the weakest, and then dipole, and hydrogen ion dipole, and hydrogen bonding in order of strength. But this is not the only factor that determines the strength. I'm telling you right now, on your test, you will have a case where you have a non-polar molecule that has a stronger intermolecular force than a dipole. Because it is not the only. The other factors, you should be comparing two substances with the same mass, the same shape. If you are comparing a non-polar that is very, very large with a polar that is very, very small, it may happen that non-polar has a stronger force than the polar. So you have to be extremely careful. It's not always that those are in that order of strength. Here's an example of London dispersion. The amount of distortion of the electron cloud is referred to as polarizability. I need for you to get used to that word because you should be using it in your essays. The strength of London dispersion increases as the number of electrons increases due to increasing polarizability. This is very common question on tests. Very common, listen carefully. If you have two non-polar molecules, they ask you which one is stronger. The one that is larger, the one that has more electrons is stronger. Okay? Most books will tell you the one that has more mass. It happened to be like that, but it is not the explanation you should be using. You do not use the mass as an explanation. What you should be using as explanation is the size of the electron cloud. Because you have more electrons, the electron cloud will get more distorted. Okay? Let me repeat. You do not use the mass as an explanation. You use the size of the electron cloud. More electrons, more distortion in the electron cloud. Alright, and then I need for you to, again, use that word. Use that big word so people reading your test will see that you know what you are talking about. The one that has more electron is more polar, polarizable. Use that word. Okay? Make sure you use it, but make sure you use it right. The one that has more electron is more polarizable. Okay, covalent bond, I already discussed this quickly. The bond between H and the Cl is covalent. It is intramolecular force. It is much more stronger than the inter between those molecules. And we already discussed the hydrogen bond. Oxygen of one molecule, hydrogen from the next one. Nitrogen from one and hydrogen from the next one. So you need make sure you know your... Alright, so almost there. Almost there. This is a graph to show you, because of hydrogen bonding, how the trend is completely different here. Let me show you what's going on. I even put a periodic table right here for you. This is a trend in this is the period as you go down, how the boiling point will increase. So let me show you what's going on here, and then two more pages and we are done. This is chlorine, bromine, iodine. Okay, chlorine, bromine, iodine. As you go down, you have a larger size of atom. The intermolecular force will be stronger, and then you have a higher boiling point. But let me reset and show you what's going on. Okay, very nice trend, carbon, silicon, germanium. You're going up. This is chlorine. Oh, where are we? Chlorine, bromine, iodine. Very nice trend. But look at water. Look what happened with water. Even though water has a low molar mass, it is small. Look at the boiling point, how high it is because of hydrogen bonding. Okay, all of those, because of hydrogen bonding, they do not follow the strength. Extremely high boiling point. Hydrogen bonding. Okay, 2 pages, type of crystalline solids. There are 4 types of crystalline solids that you need to know. Molecular, usually soft with low melting point and poor conductivity. Covalent network, very important. Covalent network, very hard, very high melting point and poor conductivity. A good example is diamond. You will have this on the test. And you have silicon dioxide. Those are examples of covalent network. Even though intermolecular forces are London dipole, hydrogen, ion dipole, but those substances, covalent network, they have a covalent bond, which is extremely strong. Okay, so not all covalent compounds have covalent network. Has to be diamond, has to be silicon dioxide, very, very few substances. That's why they are so hard and they have so high boiling and melting point. So you have ionic solids, they are hard, brittle, high melting point and poor conductivity as a solid. Metallic, they are made of metals. Okay. Okay, classify each of the following substances according to the type of solid. This is a metal, it has to be the metallic solid. Carbon dioxide, it has to be a molecular or covalent solid. Covalent solid, lithium fluoride, this is an ionic compound, so ionic solid. Krypton, it is a, what is this one? Covalent. Covalent, so we don't have any covalent network. So remember, it has to say covalent network to be the graphite and the silicon dioxide. Okay, thank you very much for your patience. So at least we don't have to come back to this unit. We are done with it. So make sure you go over the video and you have a good rest of your day. Bye.